wherein the CAE in tandem with engine tests are able to predict the life consumption of critical components like turbine blades and discs and shafts in an in situ manner. What do? They have tried to substitute a conventional approach. The conventional approach, whenever a machine life cycle is given to them, they only use the empirical cycles which are based on zero max or idle max or cruise max, and they have got simple correlations by which a mission cycle of certain duration is simply converted into the life consumption. This is a safe life approach, which is a traditional approach. In fact, most of the Indian Air Force related initiatives talk about this kind of approach. But fundamental problem is, even when a particular component is due for retirement, there is a possibility that that component might be having tremendous amount or a significant amount of life within the component. So how was the CAE applied in this case? The CAE tried to connect the practices like rain flow algorithm, by which you can simplify a mission cycle into zero max zero cycle. Then you do the damage calculation corresponding to each of these segments by employing the principles like Coffin-Manson or Smith-Watson-Topper, and calculate the fatigue life consumption corresponding to each of these legs, and you keep on accumulating the data as a function of the number of hours which the engine is subjected to in the test bed, but you don't really look up to the time consumption, the absolute time consumption as the de facto parameter. It is the data which is corresponding to the speed versus time, temperature versus time, or pressure versus time, which is going to govern the life consumption rather than the absolute time, which is the conventional practice. The fundamental advantage of this particular practice is you can use in a very ingenious manner the DOE principles and the techniques like response surface evaluation, and you can create relations between the stresses and strains, between the stress and the operational temperature, between the strain and operational temperatures. Either you can go for stress versus life approach or strain versus life approach, and you can keep on calculating the life consumption as a function of the operational parameters, not as a function of the time for which the gas turbine is tested, which in turn is tantamount to the life extension. Because if you are able to assess the life consumption, you will definitely know with 100% conviction where do you reach that point of time wherein you can say curtains down for a particular component. Now, I've been talking about the CAE practices in isolation, but when you come to the companies which for which the livelihood is the design and development of gas turbine engines, you don't see CAE community working in isolation. The CAE community in most of these engine houses work in tandem with the experimental mechanics team or SEM teams in terms of identifying the problems and providing the solutions. One thing which comes to the forefront whenever you talk about CAE is versatility of CAE techniques. Whatever will require for understanding the mode shapes of turbine blades at different frequencies, different speeds, in terms of thousands and thousands of strain gauge based testing can be done by one single analyst without spending too much of money on the resources like strain gauges or lead wires or the instrumentation. But unfortunately, incidentally, the practices which are hinged only on the CAE may go astray in many cases simply because of the uncertainty connected to the boundary conditions or operational conditions. So the coexistence of the experimental practices is the need of the hour, especially when you have a provision for getting the full field data. You can see one nice technique called thermal painting, wherein on one side you do the heat transfer analysis to create full field temperature maps of the combustor liners, and other side you can put these temperature sensitive paints on the combustor liner, and this goes through the complete series of testing. When you strip it open, it might have developed beautiful color patterns which are nothing but isothermal patterns, and by looking at the patterns straight away you can pinpoint specific hotspots which can be correlated with the results of the heat transfer analysis. So it's a beautiful approach which can synergize an experimental practice with a FEM practice, especially when you talk about internally cooled components like turbine blades or nozzle guide vanes. You tend to give a lot of importance in identifying the distribution of these temperatures across the cross section of the blade, and most importantly, you are interested in locating the specific point wherein the temperature is likely to peak. So this particular information, on one side it could be obtained from hundreds of thermocouples which may be intrusive in nature, or you can employ the thermal paints and correlate with the results of the heat transfer analysis. GTRE has somehow mastered the art of health monitoring of the turbine blades and compressor blades by getting the data from strain gauges on one side, and on another side through a non-intrusive technique called NSMS, and both these data sets in tandem with the FEM modeling will help us in giving lot of inputs in assuring the health of the components like compressor blades and compressor discs. And this is my favorite topic. In recent times, there is a digital manufacturing which has come into the anvil in terms of translating your CAD data without the usage of any fixtures or jigs into a physical tangible part. So if you can conceptualize a geometry, however complex it may be, in one singular step you can translate your design vision into a physical part. That is called rapid prototyping. How does it enable the product development, especially in case of a gas turbine engine? See, imagine that you have got a LP spline shaft, that is low pressure shaft. You have got a male shaft and female shaft, and the splines are extremely vital for the performance of the transfer of the humongous loads from the turbine to the compressor. Now, the splines are, as you are aware, do encounter many times the failures of the fillet roots. And the torsional shear stresses across the spline length is extremely important. And it's a complex three-dimensional stress analysis problem. So in one single step, you can create the front shaft and main shaft and assemble them. You subject it to torsional loading, and by doing the stress freezing technique of this particular shaft, you can easily identify the specific location wherein the stress concentration is likely to be encountered. And this particular data can be co-validated with the 3D analysis of the shafts. So this is one more beautiful case study wherein we wanted to develop an instrumentation unit called a portable telemetry unit. Most of you are familiar with the concepts of telemetry and telecommanding, would be aware of the fact that these are essential in terms of identifying the health of the system. It could be aircraft or a gas turbine engine, and it can pick up the signals from various transducers like thermocouples, pressure gauges and strain gauges, and keep transmitting the data to the ground station. Fundamentally, the packaging of this particular unit is extremely important. It has to be limited to very small dimensions, and the electronics need to be contained to less than 70 degrees centigrade. And you can see a tremendous opportunity for application of CAE practices in packaging it, minimizing the weight, and also ensuring that the heat, the temperatures do not exceed 70 degrees, because that is the threshold beyond which electronics do not become reliable or not reliable. So how was the CAD and CAE and digital manufacturing were used in concurrence? So we created a complete CAD model of this particular telemetry system, and after creating the CAD model, we transferred all the CAD models into physical prototypes using one technique called fused deposition modeling out of thermoplastic material. And then we conducted, on one side we were able to predict the hot spot, which is more than 70 degrees on this inner routing using the heat transfer analysis. On the other side, since the parts were made within a couple of days, we were able to mount a thermocouple and identify whether or not the hot spot which has been vindicated by the FEM is really a hot spot. And there are also cooling pipes which are responsible for cooling of the shell, and even in this case we created small cooling pipes out of rapid prototyping, and we were able to do the heat transfer tests by embedding them into the external periphery. And ultimately, the strain wheel or strain sensor, which is the core element of this particular telemetry unit, you can see how the stress distribution was assessed by FEM. On concurrently, we were also able to mount a number of strain gauges, and this data correlated so beautifully that we didn't have any problem in translating this design into a metallic part made out of titanium alloy. So this is one more case study wherein traditionally when you are talking about gas turbine engines, let there not be an impression that you should only talk about the components, but also you can help even the test rigs which are essential for analyzing the integrity of the components. In this case, the test rig was meant for evaluating the integrity of a long slender shaft called instrumentation transfer tube. It's about 1.8 meters in length and the wall thickness is less than 3 mm. So what is that we did was we created a CAD replica of the entire test rig, but we had our own uncertainties in terms of whether or not this particular test rig will function at about 12,000 RPM with just 2 support points. And most importantly, this component is a Class A item. What does it mean? In case this component fails, it will be catastrophic to the entire mission. So we created a scaled down replica of the same. We rehearsed the complete assembly disassembly procedures, including the making of the tools. And with this kind of a confidence coming in with a virtual prototype, we were able to jump into the actual testing, and we were able to complete about 600 hours of testing on the instrumentation transfer tube. This is what it is. So the actual rig looks like this. And one more case study wherein you can see the coexistence of CFD studies for identifying the flows, and the CFD model, rather the CAD model which was used for creating of the combustor, was also used as the input for creating a transparent stereolithography replica of the combustor, and it was tested in a water flow facility, and the pressures were picked up from various locations in the combustor, and the data corresponding to these pressure drops at various places was provided as an input to the CFD practitioners in terms of assessing the velocity vectors. Okay, I am almost in the concluding phase of the presentation. I think maybe there are about 4 or 5 slides. I had an occasion to go through a recent publication of NAFEMS, which has carried out one white paper study called FENet. And more than 900 respondents from the aerospace sector were interviewed to identify what are the future drivers for the CAE analysis. The first driver you can see, shorter development time. The second driver, which is extremely important in these times wherein you see that the price of petrol barrel is always on the upsurge, so reduction in the fuel consumption. And third and equally important criteria is safety requirement. And fourth requirement, which may not be obvious to many beginners of CAE, but very, very important once you get into the real world of engineering, interfacing between the analysis results and the testing requirements. Then the fifth one is very, very fascinating, dynamic data driven analysis. What does it mean? Typically, the parameters of a FE model are constant once the simulation process is on. It could be boundary conditions, it could be anything corresponding to the load distribution. Imagine that there is a test going on and you keep getting the input from the test in real time and provide it as an input to the analysis. So through the synergistic combination of inputting the test parameters from real world into the analysis, you can be controlling the simulation in a very dynamic way. And the beauty of this particular thing is it could be enabled on smartphones which you carry. So they are looking at the possibilities of implementing dynamic data driven analysis for analyzing all those situations wherein certain parameters are not known to you simply because the data is not available, or maybe they are stochastic in nature. And the next point is need for knowledge-based pre and post process, and more importantly, we are moving more and more towards an integrated approach wherein we talk about multidisciplinary design and optimization. Till now, I've been only talking about FEM practices corresponding to the gas turbine engines. And as Paul displayed, maybe it is at the UG level, PG level, or PhD level of the CAE practitioners. But what is very, very heartening is even today's student community have taken to the CAE in a big way. This particular thing was a project of a biotechnology student of our own Bangalore-based institution who wanted to develop customized implant in case of a patient who has lost a major portion of his pelvic girdle in the right side. And what is the challenge here is he has to develop a customized implant, because in these cases you don't get the implants. So he started working with an orthopedic surgeon on one side, another side with a CAE practitioner, and he came to us with reference to some testing of this particular pelvic girdle. And you can see here, he started developing a lot of models, first concept, second concept, third concept, so on and so forth. And when you do this finite element analysis, the biggest obstacle will be how to get reliable models for the bone structures. And what are the uncertainties here? The soft tissue growth, whether or not you are capable of taking up, whether or not you are considering the cyclic loads to which this anatomical structure is likely to be subjected to. With all these things, he developed an implant design which was tested, and he identified the stress concentration factor very close to the Fashioner holes, and he was immensely surprised when he gave a model of the same thing to us, which we translated into a stereolithography model, and in the worst case scenario of this particular thing was very, very close to what he predicted. And now he is marching towards medical trials of this particular implant. So if you see, this kind of a multidisciplinary approach is apparent not only in case of a gas turbine engine, but also it is translating into the bioengineering or consumer goods sector like what it was illustrated before. Let us end this talk on a very, very positive note. NASSCAM is a revered professional body of India, and they got the consulting firm called Booz Allen Hamilton to do a survey on the possibility of business opportunities for engineering services, which they predicted that it will be worth about 1.1 trillion by 2020. And immediately I have to draw your attention to the fact that this particular market is highly fragmented, with the major players like automotive and aerospace garnering about 25% of the market. And pitiably, in spite of the fact that we have got very good mathematical background, analysis background, and about 14 lakh engineers passing out of 3,500 engineering colleges, our current share in the engineering services is just about 12%. So where is the need? So we need to overcome this kind of inhibition that we need to be doing only secondary engineering services. We need to get into the design services, and if you can bring in some quality into the analysis practices, it has been predicted that from the current 12% level, we can hope to grow to about 30%, and which in turn can lead to 2 lakh plus job opportunities in the CAE world. And this particular market could be as high as $25 billion from not only the indigenous engineering services, but also from offshoring the engineering services. So I just want to conclude my talk by saying that the analysis professionals, of which we are all representatives, can play a vital role in ensuring an inclusive and sustainable growth of the business at the ground level and technological growth of the country at the large level for achieving higher and higher echelons in the years to come. Thank you so much.
For an exciting talk. I mean, lots of us in the service industry do have this disconnect with some of the hardware, the experimental side of things. While we do get to read about them, I think it's fascinating to hear that we are actually doing that within our own country. And I think all the efforts that have gone, and Dr. Sundararajan has shared a lot of stories of his experiences at GTRE. You could take a whole day in terms of explaining all those fascinating experiences in building a complex system like the Aero engine. I also am personally fascinated with this whole concept of dynamic simulation, which he mentioned about work getting done on the iPhones and smartphones. I was just wondering, all our engineers, they keep asking for bigger and bigger hardware. So it'll be very easy for a service company to just hand off iPhones and expect them to work even on their way back home. So this is something that we need to really figure out. But on a serious note, I think what it means is that even from a personal experience, we've seen that just because we have bigger and bigger machines, I see a lot of engineers trying to put bigger and bigger meshes. A million nodes is nothing nowadays. They want 10 million nodes and 100 million nodes. But I think the same problems were being solved with probably 100,000 elements about 10 years ago. So while there are obviously technical reasons for doing it, but I think it's just that you must be able to understand what is the physics behind it and then take it to that. Sir, in appreciation of your presence here in the talk, would like to give you a small memento. Thank you so much. We'll break for tea and come back in about 10 minutes and resume the sessions. Okay, the next speaker for today is Paul Witt. He's our center manager at the Cincinnati operations in US. Just a brief introduction. Paul is the manager for the Cincinnati Engineering Center in the North America OBU of Quest, a group of 53 aero and fluid system engineers. The Cincinnati Center focuses on aerothermal simulations for the gas turbine and related industries with GE Aviation, United Technologies, and Siemens Energy as primary customers. Secondary air systems modeling, heat transfer, aerofoil design, and engine integration are the key areas of expertise for the center in the US. Paul started his engineering career as a scramjet combustor design at NASA Langley for the NASP and X-43 programs. He moved to a small gas turbine engineering company, ASE Technologies, as a project engineer in 1997, rising to the role of project manager. ASE merged with Quest Global Services in 2009, and Paul moved into the role of program manager and then was promoted as the center manager in October 2010. Paul was granted his BSc and MSc degrees in aerospace engineering from the University of Missouri-Rolla in 91 and 92 respectively. Paul, thank you for making time here. Over to you. Before that, of course, one of the formalities, I'd like to hand over a bouquet to you, Anshu.
Thank you.
Over to you, Paul.
Thank you. So I'd like to thank Dr. Chandrasekhar for really a great introduction to my presentation. He gave a very nice horizontal view of how CAE fits into the gas